Welcome to the Explainer. Today, we're going to tackle a concept that's, well, at the heart of how fast your favorite apps run. It's called BigONotation, and it's a huge deal in computer science.
I mean, we've all been there, right, haven't we? Just staring at that little loading spinner wondering what is taking so long. Well, a lot of the time the answer comes down to how efficient the code is. And to really get that, we need to talk about something called algorithms.
Okay, so what's an algorithm? The easiest way to think about it is like a recipe. It's just a set of steps a computer follows to get something done. Like sorting your email, or finding you the quickest way to work, or figuring out which movie to recommend. And just like with cooking, the quality of that recipe, that's what makes all the difference in speed. All right, so how do we measure which recipe is better? You might think, easy, just time it with a stopwatch. But that's actually pretty misleading. I mean, a program that seems super fast on a giant supercomputer could be painfully slow on your phone. So counting seconds just doesn't work. We need a totally different way to compare them.
See, the real question isn't how fast is it right now with just a little bit of data. Honestly, that's the easy part. The real test, the thing we really care about, is what happens when things scale up, like way up. How does our recipe hold up under all that pressure? And this is the absolute heart of it all. The question is, how does the runtime grow as the input size increases? Think about it. If you double the amount of data, does the work double? Or worse, does it quadruple? Or, in a perfect world, does it barely change at all? This whole idea is called scaling, and it's what separates really great code from, well, not so great code.
For example, let's say you're searching a list for a name. If there are only 10 items on that list, pretty much any method you use is going to feel instant. No problem, right?
But what happens when that list has, say, 10 million items? Whoa. Now all of a sudden, the recipe you chose matters a lot. A bad one will just grind to a halt, while a really efficient one will still give you an answer in a flash.
So there's a formal name for this whole idea of measuring how an algorithm scales. It's called asymptotic analysis. Sounds complicated, right? But it's really just a fancy way of saying we're looking at how the algorithm performs when the input size gets unbelievably huge, like when it's heading towards infinity. It helps us predict how our code is going to behave when it's really put to the test. Okay, so how do we actually talk about this stuff? We need some kind of special language, right? A shorthand to describe how things grow. And that, my friends, is where BigONotation comes in. It's basically a way for us to categorize algorithms and compare them.
What BigO really does is describe the worst-case scenario. It gives us an upper bound on how long things might take. It's answering the question, okay, in the absolute worst possible situation, how bad can this get as my data grows? It's all about planning for the toughest possible job.
Let's dive into some examples. And we've got to start with the absolute best of the best, the gold standard, O1. We call this constant time.
This is the holy grail. I mean, it's what every developer dreams about. An O1 algorithm takes pretty much the same amount of time no matter how big the input is. 10 items, 10 million, doesn't matter. The time it takes is, well, constant. Okay, next up we've got a super common one, and it's generally considered really good. It's called ON, or linear time. And this one just makes a ton of sense, right? The runtime grows in a straight, predictable line with the size of your input. So if you double the input, you roughly double the work. It's a really solid, common goal for efficient code. A perfect example of this is just searching through a list, one item at a time. In that worst-case scenario, the thing you're looking for is at the very end, so you have to check every single item. The amount of work is directly tied to the size of the list, which we just call N. Makes sense. All right, now we're starting to get into the danger zone. This is ON squared, or quadratic time. Yeah, this is where performance can really fall off a cliff. With quadratic time, if you double the input size, you actually quadruple the runtime. This kind of thing often happens when your algorithm has to compare every single item in a list to every other item. And as you can probably guess, that gets really slow really fast. And this chart just lays it all out perfectly. Look down in that green zone. Those are our star performers, like O of 1, and another great one, O of log n, which is super efficient. They barely even curve up. Then you have O of n, our good straight line, but then look up in the red zone at O of n squared. It just shoots straight up. That's a massive jump in work for just a little more data. That is the performance cliff we're always trying to avoid. Okay, so theory is one thing, but let's see this in action. How does this actually play out in the real world? A perfect way to see this is by looking at different ways to sort a list of numbers.
So let's put two sorting methods head to head. In one corner, we have selection sort. It's simple, easy to understand, but it's O of n squared, so it's in that bad performance zone. In the other corner, we have merge sort. It's definitely more complex to write, but it's way faster at scale, clocking in at O of n log n. This is the classic trade-off you see all the time, easy and simple versus powerful and fast. And here is the proof in the pudding. This graph shows the actual time it takes. Just look at that merge sort line way down at the bottom, it's practically flat. It's so fast you can barely even see it. Meanwhile, look at those other O and N squared algorithms just climbing and climbing. As the list gets bigger, the difference isn't just a little bit, it is absolutely gigantic.
So you can see this isn't just some abstract thing for computer science class. Understanding Big O is absolutely fundamental to pretty much all the technology that we use every single day.
I mean, think about it. Every time you use a map app to find the fastest route, that's a super efficient algorithm at work. When Netflix recommends a movie, its engine is sifting through huge amounts of data. And of course, search engines, sorting through trillions of pages to give you the best results. None of this would even be possible without developers picking algorithms that have really, really good Big O efficiency. And, there's this quote that I think just nails it. It talks about great algorithms being like the poetry of computation. And that's so true. There's a real art, a real elegance to finding a smarter, more efficient way to solve a tough problem. It really is the art behind the science. Which kind of leaves us with one last big thought. When you look at the huge challenges we're facing, things like mapping the human genome or modeling climate change, these are all massive, massive data problems. And solving them isn't just about building faster computers. It's going to depend on us discovering even more brilliant, more excellent algorithms.